A very good evening to one and all present here. IEEE Mysore subsection with IEEE Bangalore section, IEEE Information Theory Society, Bangalore chapter, and IEEE Circuits and Systems Society, Bangalore chapter is organizing its second webinar on MIMO communication 5G and beyond. I, Sri Harshita P. from the Department of Electronics and Communication, take this opportunity to tell a few words about IEEE Mysore subsection. IEEE Mysore subsection, established in the year 2020, is one among the three subsections of IEEE Bangalore section. The objective of IEEE Mysore subsection is to conduct various student and professional activities like invited talks, student internship, workshops, and flagship conferences. IEEE student branches of Mysore, Mandya, Hassan, Kodagu comes under IEEE student. The subsection aims at enhancing professional networking and promoting humanitarian activities. IEEE Mysore subsection was inaugurated by Ms. Susan K. Land, IEEE President, USA 2021 on 21st December 2020 and delivered the inaugural address. It's an honor for me to welcome our speaker, Dr. Emil Björnson, IEEE Fellow, Professor of Wireless Communication, KTH Royal Institute of Technology, Stockholm, Sweden, to enlighten us with his knowledge. A hearty welcome to you, sir. I hearty welcome you, sir. I'd also like to Dr. Deepa Shanoy, Chair, IEEE Bangalore Section and Professor, UVCE, Bangalore. A hearty welcome to you, ma'am. I would like to extend my hearty welcome to Dr. Parmesh Achari BD, Professor and Head of Department of Telecommunication Engineering, Chair, IEEE Mysore Subsection, and Chair, IEEE ITS Bangalore Chapter. I welcome you, sir. I'd like to welcome Dr. Jalja S., Chair, IEEE CAS Bangalore Chapter, Associate Dean, BIT Bangalore. Welcome you, ma'am. I'd like to welcome Dr. Jalaja S., Chair, IEEE CAS Bangalore Chapter, Associate Dean, BIT Bangalore. Welcome you, madam. I also welcome office bearers and execom members of IEEE Mysore subsection, IEEE Bangalore section, IEEE Information Theory Society Bangalore chapter, IEEE Circuits and Systems Society Bangalore chapter. I'd also like to welcome participants of today's webinar. I'd also like to welcome all IEEE staff and student coordinators for this webinar. I welcome all my fellow students and friends. Once again, I welcome each one of you present here. Now I request Purti B to take over the session and introduce our today's speaker, Emil Björnson.
Good evening, everyone. I'm Spurti from Electronics and Communication Engineering, GSSS Institute of Engineering and Technology for Women. It's a great honor for me to introduce our today's speaker, Dr. Emil Björnson, sir, who is a professor of wireless communication at the KTH Royal Institute of Technology, Stockholm, Sweden. He is an IEEE Fellow, Digital Futures Fellow, and a Wallenberg Academy Fellow. He has a podcast and a YouTube channel called Wireless Future. His research mainly focuses on multi-antenna communications and radio resource management, using the methods from communication theory, signal processing, and machine learning. He has authored 3 textbooks and has published a large amount of simulation code. He has received the 2018 IEEE Marconi Paper Award in Wireless Communication, the 2019 EuroSIF Early Career Award, the 2019 IEEE Communication Society Fred W. Ellersick Prize, the 2019 IEEE Signal Processing Magazine Best Column Award, the 2020 Pierre Simon Laplace Early Career Technical Achievement Award, the 2020 CTTC Early Achievement Award, the 2021 IEEE ComSoc RCC Early Achievement Award. He has also received 6 Best Paper Awards at the conferences. It's honor to have you with us, sir. I request all the participants to put their queries in the chat box, which will be answered at the end of the session. Now, I request Emil sir to take over the session.
very much.
Yeah.
So it's time to start then, I suppose.
Yes, Professor.
Let me try to share my screen here.
Yes, it's visible. You please make it full screen.
Yes, like this.
Yeah. Yes, it's okay now.
Great. So thank you very much for the kind invitation and introduction, and thank you to everyone who is attending. So it's great to have this chance of meeting people all around the world, even if everyone is locked into the countries in the current situations. So today I will talk about one of my favorite topics, MIMO communications, and I will talk about the history of it and what is done in 5G and beyond. So I will just turn on my laser pointer here, and the outline of my talk will be that first I will spend some time talking about the cellular technology. What is mobile technology more in detail? How should we understand it in order to understand the benefits that we can get from having multiple antennas? And then I will go into more in detail. What is beamforming? How do we achieve beamforming? And how is that related to what we call MIMO, or multiple input, multiple output? And then when we know what MIMO is, what is massive MIMO and what role does it have in 5G? And then taking that into account, I will speculate a bit about what I think will happen with this technology beyond 5G. What are the research topics that are popular here? And I think I'm not the only one who is recognizing 3 different areas: cell-free networks, reconfigurable intelligent surfaces, and physically large arrays. And in some cases, people have different names, but they mean the same things here. And yeah, I'm conducting research in all these areas myself as well, and here's some of my funding agencies. But let me get started then and talking about cellular communication. So what I show here on the right is how a traditional base station, maybe 3D, 4D base station, looks like. And you see the big antennas here. There might be 1 meter tall or something like this. And what we are really seeing is that there are antennas panels pointing in 3 different directions, each of them covering 120 degrees each. And they are then used to serve users in different directions. And the way that we are building cellular networks is then to put these things up at different locations, and then you are covering a certain region of the city or the rural areas where users are connecting to the space station, particularly one of the sectors. And this is, of course, an old technology. We are now at the 5th generation. So what is really the new thing? Well, the new thing is generally that, well, first of all, that we might want to have more services. We are moving a lot of things over to doing it through mobile telephony instead of using it in other manners, like we are watching video and streaming instead of video broadcasting. But also, we see that the traffic is growing all the time. So here's an example that I extracted from the Ericsson mobility report. It's a mobile data traffic in exabyte per month in different regions of the world. So you can see they have a North America region, they have an India region with neighboring countries, and you can see that the traffic is growing rapidly. And some years ago, the India region was surpassing North America in terms of traffic, and it continues growing, maybe with 25 to 30% per year, which means that even if we don't look for any new services, we just want to use the same thing as today, we are using these services more and more. So if the technology is sufficient today, well, then tomorrow or 5 years or 10 years from now, we will need to have much higher capacity in our networks to deliver the traffic that people are asking for. So to quantify the traffic capacity, the number of bits per second that we can deliver in a particular area, like the yellow region here, well, we can break this down in bits per second per square kilometer into 3 different factors. One is what I call the cell density. That is the number of cell areas like this that we are creating per square kilometer. And that is something you can vary by putting up more base stations. Then we have the available frequency spectrum, it measured in hertz. So you get license for a particular piece of spectrum, and that is essentially telling you how many small pieces of information you can transmit every second. And finally, there is something called a spectral efficiency. That is how much information you can pack into each of these small packages. And it's measured in bits per second per hertz per cell. And if you multiply these units together, you get bits per second per square kilometer. So this is a way of measuring the traffic capacity of a cellular network. And why do I break it up like this? Well, because these are essentially the 3 different things you can touch in order to improve the traffic capacity. Densify, use more spectrum, improve the efficiency of the spectrum you're having. So let's have a look at what we have traditionally done when it comes to improving the network technology. Here I'm showing a scenario, it's just very simplified, 4 cells, and they're square shaped to keep the symmetry simple. In the center of each square, there's the base station tower, and then you can move around this area. And then the data rate in megabits per second that the user would get when you are somewhere in this region is varying as this 3D graph is showing. If you are in the center of the cell, you're close by, you get a strong signal from your base station, and therefore you get a high data rate. In this case, it's up at 80 megabits per second or something like that. Then as you move away, it becomes weaker. And then when you are at the edges of the cell in between, you have a weak signal and you might be interfered by the neighboring cell tower. And that's why you get the smallest numbers. So if this is sort of a baseline scenario, what could we do? Well, we had these 3 factors. Let's start with one of them. Let's say that we are using more bandwidth. What this means that according to the sampling theorem, the more bandwidth that we are using, the more small pieces of information we can transmit, the more samples per second we're having. And that means that if we are increasing the bandwidth by 10 times, then the maximum data rate that we can get increases from 80 to 800. So but you get curves that goes up and down like this still. And at the edges of the cell, it doesn't really get better. You only benefit really when you are in a situation where you already have a strong signal. And you also will have to transmit with more power, 10 times more power, in order to sustain even this trend where it goes up and down. Otherwise, it would be even worse, falling down even more quickly at the edges of the cells. But it is a good way at short distances to improve the data rates. Another thing you can do is to put our base station more densely. Instead of having 2 by 2 here in the square area, let's instead have 8 by 8. And then you have many more of these sort of towers going up and down, up and down. So yeah, you have a bigger chance of being close to a base station, but at the same time, you are very quickly close to a neighboring base station, you get interfered. So it also goes up and down like this. Both of these methods will, on the average in your network, enable you to transmit more data. And this is what we have been doing a lot in the past decade when we have been improving our networks. Use more bandwidth and deploy more base stations. But the shape of this is really determined by this 3rd factor that I was having, the spectral efficiency. And I think that we would like this to be more flat over our areas in the future, because we are not really limited. I mean, 800 megabits per second, if you can get that is clearly enough for most use cases. We would like it to be smaller variations. So I mean, you're not complaining in the best case about that you don't have enough data traffic. The problem is that when you have a poor signal, you are not having good enough data rates. So I think this is shape that are important. So what can we do about the shape? Well, the general issue here is that when you have a transmitter that sends out signals, then your receiver is at a particular location. And the fraction of the transmitted power that reaches that receiver is proportional to 2 things: the size of your receiver and how far it is. So essentially, ideally, a sender sending out a signal, like a balloon that you blow up, and the energy lies on the surface area. So the surface area of a sphere with the radius r is 4 pi r squared. And then you compare that with the antenna area in your phone. And that ratio is the fraction of the send power that you receive. And already at 1 meter distance, r is equal to 1. And we pick a typical cellular frequency, like 3 gigahertz that we're using in 5G. At 1 meter, you're receiving 0.001% of the power. At 10 meters, if this is a line of sight scenario, so you see it directly, you lose a factor 2 due to this. You increase by 10 times, but you have a square here, so you get 2 more zeros, 0.00001%. And as soon as you don't see the base station, there's other kinds of objects around, you'll lose even more. So my main point here is that we are losing a lot of the power along the way. It's a tiny fraction that is received in reality. What can we do about that? Well, that is really why it was falling off so quickly when you are at the edges of the cell. Well, one option would be that everyone walks around with a bigger phone. Maybe that is not what you want to have. You don't want to have a tablet in your hand. So the other option would be that we are instead transmitting in a more directive manner. So even if you're only receiving a fraction of the power that is proportional to the size of your antenna, maybe at your part of the sphere, you have a larger fraction of the power. So how can we achieve that? Well, this is not really nothing new. These tall antenna towers that I was showing on my first slide are directive antennas that have a fixed transmission. You're not aiming up in the air. You are not aiming 360 degrees. You are aiming down to earth in a 120-degree sector. And that is what I'm showing here, a fixed sector antenna. This particular example is a so-called 16 dBi antenna. It means that you have 16 decibels, or 40 times stronger signal than you would have if you're transmitting all directions, but only if you happen to stand in the center of where the antenna is facing. So lucky users standing here will get a stronger signal. So what is the problem with that? Well, the problem is that we only get that strength if you happen to be at the location where we are aiming. So these unlucky users here that still have this base station as its closest base station, but they are behind the building, they will not benefit from this antenna gain. In fact, they might lose, because when we are focusing the energy here, that means that we are transmitting less in other directions. We are not putting more power into this, we are just redirecting it. So ideally, we would like the signals here to bounce off this building in a directive manner and then reach these users. And to do that, we would like this beam, this directivity, to be adaptive, to change it depending on where the user is, to help mitigate the losses along there. And that brings us into the topic of beam forming, and later the thing that is MIMO. So let me explain in a nutshell what beam forming is. You have two antennas here transmitting signals, and when we are transmitting, it's like waves that are propagating into the air, and it's a sphere that is expanding, but I'm showing here in 2 dimensions. So you see the green waves here transmit at the same time, the gray at the same time, the orange at the same time, and so on. And if you are at different locations here, you will get a superposition, an addition of these 2 waves from the 2 antennas. And depending on where you are, they will either arrive in phase at the same time and build on top of each other, or they may cancel out each other or something in between. And what we can notice is that the green lines are, and the gray and the orange are intersecting here. So if you are upwards here in this direction, this is where the 2 waves will actually be received in phase. So you will see a so-called constructive interference upwards here. Another way to show that is the following. Say that the 2 antennas are actually transmitting with no particular directivity. They are spreading out the signal energy in all directions equally. But if we start to measure the signal strength in different directions here, it will still be as if we have a stronger signal upwards than in other directions. It will look like the antenna is creating a beam, a directive signal upwards, because the 2 antennas are transmitting the same signal at the same time. And this is essentially what this big antenna panel was already doing. So where is the adaptiveness? Well, the adaptiveness happens if we let one of the antennas transmit slightly later than the other one. In this case, the right antenna here has transmitted its signal a bit later, which means that now we see the intersection is here, here, and here, and it's up towards the right here where we are getting the constructive interference. So if we are now still transmitting with antennas that have no preferred directivity, but you measure in different directions, what you will see is that the signal is strong up to the right here and weaker in other directions. So we are purposely creating a directivity up to the right here. How do we achieve it? Well, we let still the two antennas transmit the same signal at the same time, but with different delays, which can also be viewed as different phase shift if we are talking about sine waves. And that is creating deconstructive interference. So this is the principle of adaptive beamforming. Transmit the same signal from multiple places, but with phase shifts or delays so that in the direction where we would like to receive it, we get a strong signal. For example, if we would transmit with, say, 2 antennas, we get twice the strength. If we have 32 antennas, we get 32 times amplification, not because we're using 32 times more power, but because in that particular direction, we get that much more stronger signal and less in other directions. Is this a new thing? Well, actually not. Here is a patent from 1920 by actually a Swedish researcher, Ernst Alexandersson, but he was working in New York at the time for General Electrics. And I'm not going to read everything out loud here, but he talks about if a system consisting of a plurality of separate radiators is controlled in such a way that the relative phase of the oscillators from the individual radiators is made to combine in a predetermined desired way. You see, it sounds very much as my example. Having 2 antennas transmitting with different phases, so you create constructive interference in the desired direction. So this is something that has been known for over 100 years. And this guy, Alexandersson, he was also sort of recognized by IEEE in 2015 for sort of being one of the early people. And I think he's not as known as people like Maxwell, for example, or Marconi, and people who were sort of inventing a lot of the basic theory. But he was one of the engineers who was actually building things. One of the things that is still existing here in Sweden is something called the Grimeton radio station, which contains these, I think it is 6 tall antennas that was transmitted, that was used to communicate over the Atlantic to the US in 100 years ago. So it's still operational. It's on the UNESCO World Heritage Site, so you can come to Sweden and have a look at it. What is then MIMO communications? So multiple input, multiple output is what MIMO stands for. Well, the idea that were showing up in the late 80s and early 90s was that if we can create these directed transmissions in the side direction, we can actually also transmit in more than one direction at the same time. And here is a paper, I think it is from 1990 or 1991. You see base stations transmitting these beams towards cars in different directions, because at that time, mobile telephony was really for car phones. But yes, this is something at that time was called space division multiple access. Today we call it more like multi-user MIMO. We are having multiple inputs. These are the antennas in the array. We have multiple outputs. These are the receiving devices like this. And what is then the motivation of transmitting several signals at the same time? Well, if you can talk to multiple people at the same time, well, then you get more information for your system. So here's an example of this spectral efficiency in bits per second per hertz I was showing. And I have some assumptions around the channel propagation that I'm considering. But the main idea here is that I'm changing the number of users. And I have one curve here where I'm changing the number of users so that the number of antennas at my base station and the number of users I'm having is growing proportionally. And you can see that as I'm adding more user, I get more data through. If I have twice the number of antennas as users, M is antennas, K is users, then I get an even quicker increase. 4 times the number of antennas as users, I get even quicker increase. 8 times more antennas as users, it grows even more quickly. What is the reason for this? Well, it is actually the thing that the more antennas we have, the more narrow our transmissions are. So if you would like to transmit to many users, you would like it to be like illustrated here. Narrow beams focus on users and a lot of empty space in between. And that is happening when you have many more antennas and users. Let me show you this in a different way. Here is a continuation of my previous example. 4 antennas transmitting the same signal, but with different delays in such a way that we are forming a beam upwards in a particular direction. If I would like to serve 2 users with the 4 antennas, well, 2 things are happening. I need to share the power between them. So you see that the height, the strength of this beam becomes only half because I'm splitting the power between them. But otherwise, the shape of the beam, the blue one is the same as before, and now I'm transmitting a beam in opposite or different directions up here. So I can have one user here, and you will be able to serve both of them. If I would like to compensate for this half power because you're splitting it, what you do is essentially that you, at the same time, as you go from 1 user to 2 users, you also double the number of antennas. And then we get the same strength in terms of the signal to 2 users as before, but so you're compensating for dividing the power by having more directive transmissions. And you can also see that the beam width here is smaller. So these are actual beam patterns that you can compute that I'm showing you. But as I was alluding to, people talked about this already in the 90s and 2000s. Why am I talking about it now? Well, there were experiments and even some commercial deployments in the 2000s. Here is, for example, a photo from Arraycom. If you go to Tokyo now, you can still see this antenna arrays. There are, I think it's 12 antennas in a circular fashion that you can still see on some rooftops. So there were a few deployments, but there were no real commercial success. Why? I think there were several reasons. One was that it was cheaper to deploy more hardware. And another thing was that you have many antennas, you have a lot of cables, you have boxes here, you need to have as many boxes and cables as you have antennas. And yeah, some other reasons is the following, I think. One was that at that time, what did we use our phones for? Well, we actually made phone calls. Circuit switched voice service is what we were after. So the number of bits per second that we can transmit wasn't that large. The important thing was that we could just let many users access at the same time, and that we can achieve in different manners. The data rates are rather low for phone calls. It was complicated to build the hardware. As I was mentioning, you need a lot of components, and the hardware wasn't as refined as today. And at that time, we also were very early in the communication theory that was supporting how you were going to build it. There's been huge evolution of that in the last 10 years or 15 years that wasn't available when these systems were built. And I would say the number of antennas were still fairly low, 12 antennas here, and the aim was to serve many users, but you still see the big gains when you have many more antennas than users. So despite this negative experience on MIMO, people were a bit negative also 10 years ago when people were saying, well, maybe 5G should be using a lot of MIMO technology. Some people are saying, well, we tried this out 10 years ago, it didn't perform. Why are you pushing it again now? But nevertheless, we have seen this happening. So if 4G was a lot about these tall antennas I was talking about, having a passive directivity, constant directivity, so you have to be in the lucky place in order to get a strong signal. Well, what we have today are these antenna arrays that are wider, containing not one antenna with strong directivity, but a lot of, maybe 64 small antenna elements with very little directivity. They're only pointing forward, and then we are putting them together by transmitting the same signal with different delays to form beams in different directions. And all of these things at the same time. And we can put all of the radio infrastructure today into this box. So I will show you an image on this soon. But we call this massive MIMO because there's a large number of antennas. So what is then massive MIMO? Well, the term was coined by Sata, who was then at Bell Labs around 2010. He wrote a seminal paper, Non-Cooperative Cellular Wireless with Unlimited Number of Base Station Antennas, where he was really pushing the limits on the more antennas we have, the better the performance will be. And since he was pushing unlimited antennas, people were for some while thinking, well, this is something that you cannot really achieve in reality. But I think nowadays we understand that this is still at like 64 antennas, you can get a large of these gains he was talking about. So I wrote a book that you can download from SMI book Archeries.com, which is providing the main theory for this, if you would like to learn more about that. And we were trying to have a more realistic definition here, saying that the base station maybe should have 64 antennas to be called massive MIMO. They should be able to serve many more users, say 8 users at a time. And it's still this important thing, you have many more antennas than users, because then the directive transmissions are so directive, so there's a room between that user and the direction of the next user. And what are then the point of this? Well, to recap, there were 2 things. One is that you can adaptively beamform signals, and that helps users, particularly at the edge of the cell. If you're in the center of the cell in the previous technology, you are where the fixed beam is pointing. But when you move away, you're behind the building, the signal needs to take strange routes to make it to your place, and that is when you need an adaptive transmission. And this is what I'm trying to illustrate here. We are lifting up maybe the areas in the center where we get the maximum data rate, and then we are lifting up for the entire cell. So the minimum performance in the area will be much better than in previous technologies. So more consistent performance. The second thing is that as we are adding more users that are connecting, the data rate is growing. This is what this curve is showing here. So depending on different ways of selecting your beamformings, these are things that we cover in my book. We are showing that you can add more users, and it's not like you have a party and more people are coming, the smaller pieces of the cake they will get. But it's rather like more people are coming and the cake is automatically growing. So everyone gets the same piece that they were getting if they were alone. So this is sort of the main thing, up to some point where you might be serving 40, 50 users, then it really starts to saturate, and then the cake needs to be shared. So this is one of the exciting new things in 5G that also becomes a bit counterintuitive. You say, oh, why do you deploy this new network? I don't see any faster data in my phone. No, but it doesn't slow down when there are many people around. One of the important things, if you should build something like this, where you're transmitting very narrowly in different directions, is that you need to know where to point the signal. So, because if you're just beamforming in the wrong direction, it doesn't help anyone. And there are 2 main ways of doing it. One is to have an array with antennas and that is transmitting signals in predefined directions like this. So each color here is direction. In 5G, this is called CSI, channel state information, RS, reference signals. And you try out these things, the receiver is measuring the strength of the signal and it feeds back an index. I will like the red signal here. And then you transmit to the user with that signal. So it's rather easy to implement. You have a protocol just feeding back the number of the beam here. The problem is that the more antennas you have, the narrower the beams are, so you need to try out more colors. And there is also the risk, as you're showing here, this user is in between the green and red beam, so it's not necessary that there is a perfect match, which becomes problematic when you try to serve many users, because then if it's not a perfect match, you will interfere between the users. The other option is to let the user send a signal. And it's a bit like I'm speaking now. And when I'm speaking, I don't need to tell each one of you individually something. You can all listen at the same time. And the same thing happens here for the antennas and the receiver. It doesn't matter how many receiver antennas there are. All of them can look at the signal that the user is sending, measure how it was distorted by the communication channel, and then immediately know how we should expect other signals to be distorted. So the main principle is that you transmit a known signal, a SRS or sounding reference signal. And since you know it, you can predict how it was distorted. And then you know that when you transmit data. And this is perfect when you're receiving signals at the base station. If you should be using this information to then send signals back in the opposite direction, in the downlink as we call it, then we need to use so-called time division duplex, where you're using the same spectrum for the uplink to the base station, from the downlink to the users, and switching time between them. Previous generations have been a lot built on frequency division, where you are having one band for uplink, one for downlink. But now in 5G, we are focusing a lot on the TDD, and then we can do this instead. So this is sort of the main thing to make this really work. You need to know the channel very well in order to send nice beams towards the users and protect them from interference between each other. So where do we stand today? I was in October visiting, I'm here in Kista, which is a part of Stockholm where Ericsson have their main headquarters just across the street. I was visiting their studio and looked at some of their equipment. They have a large portfolio of different base stations. Of course, Nokia and Huawei and I guess Samsung and others also have portfolios this kind. But there are a number of different base stations already. And here is one example. A 64 antenna base station weighs 20 kilos, so it's not particularly heavy. You can use this for hundreds of megahertz. You can transmit a lot of power with it, and it contains integrated circuitry. So everything like measuring the channel, decide how you should transmit to this phase shift, something like that. It's all done in this box in a digital manner. And here is me holding an array which has 32 antennas, and it only weighs 12 kilos. So it's really not massive in the sense of being big and heavy, but massive in the sense of having many antennas that allows you to transmit signals in a very detailed manner to people in different places. So this is essentially whenever someone have a massive, when they have a 5G base station, this is the technology that is in that base station today. So if you would then open up like my MIMO book or Thomas Sata's first paper on this topic, does this real hardware that we have out in real networks today perform as the theory was telling us? Well, we were studying this in a paper a few years ago by doing real so-called ray tracing not measurements, but we had, as you can see here, a simplified version of New York City. And then we had a state-of-the-art ray tracing software that's considering when you're transmitting from a base station, which object will it bounce off to reach the user to get a rather detailed description of the propagation channels. And what we wanted to see was if the MIMO theory and the real system here was performing in a similar manner. Because what a lot of the theory is considering or is disregarding, particularly Thomas Sata's first work in this was disregarding the geometry of the antenna arrays, the shape and the angles of the propagation environments. I mean, there is a certain shape here of a city, right? And this turns out to be important. So we ran the simulation. We put out in this city 16 base stations. We dropped users randomly. We were using some state-of-the-art methods in order to evaluate the performance. I'm not going to bore you with all of those details. But we did sort of the real best thing you can do according to textbooks like mine. And what I will be showing you is the downlink throughput in megabits per second that the user is getting at random locations. So there are values between 0 and 200, and there is this value here which is saying that we are varying from users in good locations up here to users in bad locations down here. And there are three curves. They are representing three things. The first thing is what Thomas Sata was describing in his early work in this topic. A very simplified channel model called IID, or independent and identically distributed Rayleigh fading. It's the simplest kind of model you can have. And that is the black curve. Then we have two more real deployment scenarios. You have a planar array. It's a 1 meter wide and like 0.34 meters tall. So 24 by 8. So in all these cases, there is 192 antennas. And then there is an antenna array with half a wavelength spacing, and it's like 8 meters long. So it's a large array. And I would say this planar array that I have, which is the red curve here, is the closest to what we have in reality, while we could, in principle, also deploy this brownish one. So what is this curve telling us? Well, if you are a lucky user, you are getting the highest data rates. Then there is not much difference between the curves, meaning that it doesn't really matter if we use the simplified Sata models or if we are putting a real deployment with two different types of arrays. The array doesn't matter. The important thing is that we get good performance. But the difference is appearing down here for the unlucky users, the best case is predicted by Marceta's baseline. The worst case is what we actually are deploying today. And in between, we have a long array. So what is the reason for this happening? Well, the reason is that most people in a city are at different directions horizontally. Well, even if you have tall buildings, the variations in angle is rather small compared to the variations horizontally. And that is why we would like the antennas to be long horizontally, because then the beams are narrow horizontally. And this is something we will take with us now in my last part of this lecture, where I will talk about how we can evolve MIMO technology beyond 5G, keeping this in mind, what are the limiting factors still. And whenever we are looking into the future, I think this quote by Roy Amara, which had been said by some other people, I think Bill Gates said similar things. We tend to overestimate the effect of a technology in the short run and underestimate the effect in the long run. So if you start reading papers about what will 6G beyond 5G systems of the future be doing, there's a lot of speculations. But the problem is that it's very hard to speculate what we will specifically do. Will everyone go around with virtual reality glasses, or what will actually happen? And as an example of that, 3G was introduced in 1998. And 6 years later, OECD, which I guess is a European organization for economic growth, they were putting out a report where they were saying, what will 3G be used for? This is already halfway into the 3G era. And they were saying that we think that 3G will be used for video calls, for location-based services, for mobile broadband, for internet access, and for video services. And you might say, yeah, we are using mobile phones for all those things today. Yes, but I think video calling, the first time it really took off in mobile phones was when FaceTime was introduced in 2010. And that was when 4G was already introduced. And now we are using video calls all the time. But this is another 10, 12 years into the future. And yeah, we're using internet access all the time, but it was also sort of in the end of that era. So usually we are predicting things to happen, but we think that it will happen much earlier than they really happen. So my point is the following. I think if we would like to predict the future of cellular technology, we shouldn't think too much about what we will use it for. Will everyone have Google glasses, Apple glasses? Will we have connected cars? Will it be this and that? Thinking more about what can we improve in terms of the core technology to do things better than today. And then someone will find a new device, a new service that everyone wants to use in the future. And we will leave that to the future to decide. So with that in mind, I think that we should look at what are ways that we are characterizing our networks today, characterize what they are good at, and how can we improve things like that by 10 times. And I will end this lecture by going through these 3 different things: cell-free networks, reconfigurable intelligent surfaces, and physically large arrays, and say why I think these are natural extensions of MIMO technology for the future. The first thing is then what I call cell-free networks. And this is really about when you are deploying things in a very dense manner. So typically, we put out antennas around the world, and we don't have square cells. We have some strange shapes. Sometimes there's one antenna, sometimes there are multiple antennas. We divide the world into the cells, and we serve the user in each cell. And this is breaking down the complicated system into cells so we can operate in an independent manner. But the bottleneck is really the interference between the space stations. And it's very hard to deal with that one in conventional systems. But the idea with cell-free networks is to sort of turn the situation around. Instead of having this sort of invisible boundaries where if you move it over, you will move to the next space station and then you get interference in the opposite direction, we connect all of these antennas together to some kind of cloud computer that is controlling them and making sure that there is no particular cell boundaries. If you are a user here, you will be served by all of the antennas that is reaching you, and they will help you out in not getting interference. So by definition, there is no intercell interference. So to give you some example, and this is yet again from a book that I've written on the cell-free networks, I'm comparing three different things. One is to have 4 square cells in the same way as I've been illustrating earlier. Each of them have a base station with 100 antennas. The other benchmark is that I'm spreading out. Here I have 4 times 100, so 400 antennas. I spread out my 400 antennas over the area. And then I can either operate each of them as their own small cell area, or I can operate them jointly as a Cellfree network. And what I'm showing here is the spectral efficiency, bits per second per hertz, that the user is getting. And this is a cumulative distribution function. There is random variations in what data rate the person is getting, depending on where they are. Good locations, bad locations. And what we can see is that here we have the black solid curve. That is big cells with massive MIMO. If you are in good location, you get good performance. If you are in bad locations, you don't get 0, but you still don't get the maximum numbers. If you have small cells, you get the red curve, which is not that different. It will be different locations that are bad. Here is it at these edges. Here it is at the small edges around every small area. But on the average, as you move around in the cell, you still get roughly the same experience. But if you have small areas, small antennas everywhere surrounding you, and they are helping you to transmit from all directions at the same time to you, then you can increase the data rate, also in the worst cases, by say 4 times. So this is sort of the goal here of Cellfree networks. Many more antennas per square kilometer, few antennas per site, and they are collaborating to serve you. And yeah, this is my textbook where I'm talking about the theory for that. And how can you deploy something like this? Well, it might sound complicated. You put down antennas everywhere, you need to have cables everywhere. So that would be a lot of cabling. And when we were talking with industry about this, we came up with the idea that, well, if you need to have a cable from a cloud computer to a certain location where we'll put out an antenna, why not put many antennas along that cable? And this is what I'm showing here, antennas and processing units, and then a cable that would be sending data back and forth. So this is also what Ericsson is calling the radio stripe, with a bus sending data, processing or radio units, and then antennas that are sending out signals. So this will be more of an invisible place to publish it or deploy it. And I'm standing here in front of the Fontana di Trevi in Rome because the inventors of this particular idea like to picture cultural places as places where you can't put a base station today because they're too ugly. But these invisible things could be used and deploy antennas in a more dense manner. The second direction for the future that I'm believing in is what we call reconfigurable intelligent surfaces. I'm just wondering if I have a bit. Yeah, I have this slide instead. I was going to show you. So the idea here is that we are transmitting signals from conventional base stations. I'm standing here in my office, and the problem is that the base station is sending the signal through the wall. And the wall is very thick, so the signal is barely going through. But it can enter the room through the window here. And then it will bounce off the wall and maybe be reflected to the right corner here. But if we can deploy a so-called reconfigurable intelligent surface here, it will be like a mirror that picks up the signal and then reflects it towards me as a directed beam. And if I move around, the beam is following me. And how can we build something like that? Well, it's something that is possible to build. You divide your surface into small elements, which are at the size of the wavelength, for half a wavelength, a quarter wavelength, or something like that. And each one of them is connected to, for example, a diode and a controller unit. And with the diode, we can change the impedance of it. So, you know, a mirror of the conventional kind have the same, it's uniform, same properties everywhere. That's why the signal is bouncing in a particular manner. But if the properties of the surface is changing, different parts of the surface will delay or phase shift the signal to different extent. And just as we could beamform by transmitting the same signal with different delays, this surface is able to control the reflected beam in different directions by the colors here is indicating different kinds of phase shifts between minus pi and plus pi. You might have heard about this also under the name software controlled meta surfaces, because meta surface is one way of building it, or intelligent reflecting surfaces. In a way, it's a new type of relay or repeater are technologies that are picking up wireless signal from base station and retransmit it towards user. But here the idea is that instead of having a repeater or relay that's picking up the signal, amplify it and transmit it again, it is not amplifying the signal. It's more picking up the signal energy, and without amplifying it, without adding more power, it is reflecting it in a controlled manner. So in a way, it is like someone is standing with a metal sheet and bends it and rotates it to reflect the signal towards where you are. It's just that you don't do this mechanically. You instead are changing the electrical properties using the impedance. And this is something you can actually do in reality. Here's an example of that in a paper that we wrote last year. There's a 50 meters distance here from a transmitter, which is using a transmit antennas that sends a signal here. And here is a copper plate that is reflecting the signal. And here is the receive antenna. And when the setup looks like this, we're using some Wi-Fi band, then the received signal looks like this. Here, these two boxes here is where the received signal is. And you can barely see that it increases beyond the noise, which is outside the band. So you have a minus 66 dBm as the received signal power. So this is not a good setup. But what if we replace this copper plate, which is essentially like a mirror, with a reconfigurable intelligent surface, and we configure it to take the signal that comes from the transmitter and reflect it into the receiver? What do we get? Well, in this case, we can actually get a much stronger signal power at the receiver. So we have seen here that the maximum value goes from minus 66 to minus 39 dBm. So it's a 27 dB improvement here. And it's obviously something that we can build. Then it's a future idea about how you can make signals around you or make the propagation around you more controllable. Instead of just having transmitter and receiver and you get what you get, now you can adaptively change how objects are interacting with waves and make them sort of reflected towards the location where you want them to be. And what will be the main use case? Well, make signals bend around the corner into a room and then bend to the place you want it to be in order to improve coverage, to improve the signal strength in the worst locations. The last thing I want to mention is physical in archeries. And the thing we call massive MIMO in 5G might contain 64 antennas. It might be like 1 meter times half a meter. You put it on the rooftop, and then you have all these features. You can send beams in different directions. But if you zoom out, well, you put it on the rooftop somewhere. They are massive MIMO in terms of many antennas, but it actually is rather small. From a distance, it looks small. But what if you would sort of spread out antennas over an entire building like this? So it really becomes physically large. You see it, and it fills up a large portion of your field of view. You have even more antennas, but it becomes really electrically large compared to the wavelength. What can happen in those cases? Well, here's an example, a very simplified example. I have 5 antennas. I have antennas along 5 wavelengths here. And I'm transmitting and focusing the signal at the point which is 5 wavelengths away. So the distance to the receiver is proportional to the size of the surface. Of course, we can scale this up to having hundreds of wavelengths and the distance up to 100 wavelengths. What we can see here is how much is the signal strength improved compared to only transmitting from one antenna, so-called array gain or beamforming gain. And you see it in the 3D plot. So around this location where we have focused the signal, we get an amplification, and elsewhere there is not much. And this is what I was illustrating here. The signal gets strong in the ball around the receiver, and then elsewhere you don't see this amplification. And this is happening particularly when you are focusing the signals at locations which are nearby compared to the size of the array. So this happens in the so-called radiative near field. And if you're moving further away, you have a transition between this focusing at the point and coming to a location where you are focusing at the location, but the focusing is continuing behind you. And I think a good way of also thinking about this, that you take up your camera and you take a photo of someone. If you take a portrait of someone who is nearby, you get a nice blurry image behind you. There is no amplification behind you. While if you are focusing on someone who is far away, then everything towards infinity will be relatively sharp. And that is the same phenomenon happening here. Why would you like to do something like this? Well, the smaller the regions are where you can focus signals, the more signals you can transmit at the same time. And a theorem from a paper here is saying that if you have a large antenna array, then for every segment of the array, which is wavelength times wavelength sized, you can resolve up to pi signals. There is some geometric argument behind this. And that means that if you have a planar array here on the facade, which is like, it has a length L, it has a height H, you multiply the length and the height and you divide with the lambda square. Then that tells you how many segments you have of area lambda square. And each one of them can resolve pi signals. That means that you can resolve up to this number of different signals, create focused areas at different locations that could be different users that receive signals. As an example, say we are at 3 gigahertz, so the wavelength is like 0.1 meter. You have a 10 by 30 meter sized array. Well, then you can resolve up to 100,000 different signals. So yeah, an array like this can really handle massive crowds of people by just separating them spatially. So my point here is that if we try to build truly large arrays, we are very far from the limits of what we can actually do with these arrays. We can separate a lot of signals. So the question is rather, how many users do we have in an area? How rich are the channels? Are they separatable by the array or not? That brings me to the end. And I will end with this two-dimensional graph. So traditional systems have been operating at frequencies around 1 gigahertz up to 3, 4, 5, maybe up to 6 gigahertz when it comes to Wi-Fi. And we have mainly been using passive antennas with a fixed directivity. Now, with 5G, we are expanding the world along two dimensions, number of antennas and frequency bands. We are using new frequency bands, or we will use that in 5G at least, that are up around 28 gigahertz and above, called millimeter waves. We are also using more and more antennas in this massive MIMO scenario. So we are expanding the range of things that we can deal with. But it's mainly here we have been down at the conventional frequencies and using massive MIMO. Millimeter wave is so far more of a thing we might be using in the future, but for very specific use cases. But still, since more bandwidth in millimeter wave areas have been sort of talked about a lot in the media, oh, this is a new thing. There is some kind of idea that we will continue going up in frequency just because we were taking one new leap in 5G. But I personally think that the main development for the future is to evolve MIMO technology in the three ways that we're having. And maybe use more of millimeter wave frequencies, but take the frequency that we already have. The lower the frequencies are, the better they're propagating through walls and different objects. The further they go, the stronger the signal will be. And therefore, we try to use these new technologies to improve it. So physical large arrays, in order to be able to serve many users in a particular region. Cellfree networks to spread out the signals to get a more uniform service quality because there are smaller variations. You're often surrounded by a few antennas that is serving you. And when you have coverage holes, you can put up a reconfigurable surface to help you to get rid of that coverage hole. So that brings me to the end of my talk. If you can't get enough of me talking, you can watch my YouTube channel wireless future. There's youtube.com/wireless future, where I'm talking a lot about these specific technologies more, like Cellfree network, physical large arrays, and things like that. So, and I also have a podcast, Wireless Future, that you can find in all of the major podcast apps. So that's it.
Sir? Yeah, Professor, thank you. Thanks for the nice presentation. Actually, we have some few questions in the chat window. Can I read it?
Yes. Shall I read them, or do you want to read them to me, or how do you?
Yeah. Actually, okay. Okay. The first question from Dr. Sridhar Iyer. Sridhar, is it possible to unmute yourself or? Sridhar, can you unmute yourself?
Yeah, am I audible?
Yeah, please.
Okay.
Please go ahead.
Okay. Hi, Emil. Thank you for the insightful talk as always. I have a couple of questions. In fact, one of the questions you did answer on ResearchGate, but I will just put it out so that it may help someone else as well. So my first question was actually on the radio strip, which you showed on one of your slides. So it is already known that to achieve ubiquitous cell-free massive MIMO, you need a low cost and low complexity deployment. And for the same, radio strip is suggested by the research community. So you did show a little bit of the radio strip on the slide, but can you throw some more light on this kind of architecture and where the research is headed on radio strip?
Yes, so I think what I was showing was this kind of thing here, which is actually just plastic. But this was something that was shown in maybe 2019 on the Mobile World Congress in Barcelona. So it is a idea about how you can reduce the cabling, because a large of the limitations when it comes to deploying networks today is not necessarily that the radio hardware is so expensive, but it's deployment costs and hiring places to have things. So you want to reduce the amount of cabling and things like that. So here the idea is that how can you deploy something like this? Well, a lot of the developments that we have in wireless today is that we compute some things in the radio, and then we are sending things in the fiber cable to some cloud computer that is shared between neighboring base stations. And if you anyway are going to do some processing in the cloud, you can let multiple antennas or access point that are connected to that cloud collaborate. And even further, if you're going to take a cable from one place to that cloud, you can put many antennas inside of it. So then here the idea is that they are sharing the same maybe fiber cable to certain locations. Antennas can stick out of it, or if you have a millimeter wave frequency, it might be small enough so it fits on top of it. Maybe it will be like a thick internet cable or something. And then along the way, you have small radio chips similar to the ones you have in a mobile phone. You sort of build it using many chips of the mobile phone type. And when you receive a signal from a user, you receive something here, you process it, pass it on to the next antenna, and then you improved your estimate of the data signal there, and you pass it on to the next one, and you continue until you reach the cloud. And maybe there is another stripe connected to that cloud, and then you're fusing that information. So it's really about transmitting and receiving multiple locations and putting that data together using cloud computing.
All right. Oh, thanks. And my second question is one which you actually answered over ResearchGate. So it has more to do with, most of the studies are suggesting a two-stage channel estimation approach for the RIS-aided MIMO channels. So in those studies, they use let's say an iterative reweighted method to estimate the channel parameters. So do you suggest that is a good way to go about it, or Is there any better way to do it?
So I published a paper like a year ago called Reconfigurable Intelligent Surfaces, 3 Myths and 2 Critical Questions. And one of the critical questions there was really how we need to find a better way of estimating the channels. And I think what you are describing here is sort of the brute force approach. If you need to implement something, you tell an engineer what should you do. Well, probably this is what we would do. Then can we do something better? I hope so. I think what the general problem is that if the surface is containing hundreds of elements, then there are hundreds of parameters to estimate, and you can only estimate one dimension at a time. So you will have to repeat sending signals over and over again, 100 times or more, in order to observe all dimensions. You need to observe all dimensions, even with the most clever algorithms. If you haven't seen something, you can't improve it. So that makes the problem very complicated. The key would be to exploit some structure. And what structure could that be? It could be that you have some structure that is imposed by the array. I have some work around that, how arrays that are dense are actually creating ranked efficient channels. And another thing is what we did in this setup that I was showing on the rooftop with the signals. If you know that the signal is coming in from one angle and you want it to leave in another angle, really what you need to figure out is how much do you want to change the angle horizontally and vertically. And then there are essentially just 2 parameters to estimate. So if you can build algorithms that are exploiting the propagation environment with models or deep learning in a better way, then you can hopefully have a faster algorithm for reconfiguring them.
Thanks a lot.
Yeah, Professor, one more question is from the Mahadevan, whether RIS is suitable only for corporate environment or how about the individual users?
Yes, so corporate environment, individual users. So I think that one of the goals are to even out the variations. So I think for an individual user, the idea is that I think many people are noticing this thing. You walk around with your phone, you do something, and then all of a sudden, the service stops working for any reason. And the idea is to sort of get rid of those situations. And with spreading out antennas, letting them collaborate, there will be the possibility for an individual user, even if you are alone at the night, that you even out and remove those holes in coverage. I think that is useful. And when will it be useful? Well, corporate environments is definitely something. If you would replace all of the Wi-Fi stations with private 5 to 6G networks, and you let those Wi-Fi stations replacement collaborate, then you will get a better service in corporate situations. But I think also along streets, there is a lot of talk about putting up millimeter wave base stations on lampposts along streets in order to provide good outdoor coverage in these situations. And those base stations, I think, could collaborate and create the Cellfree network as well. So yeah, I think there are many use cases, and maybe among the 3 directions, this is the one that is most likely to happen.
Okay, Professor. Yeah, thank you. What about the radiation hazards in case of large antennas on the buildings?
So I'm not a medical doctor, so I cannot tell you about those things. But what I can say is that whenever we built wireless technologies, every country have limits on the radiation density and how much wireless signals that are allowed to come to a certain place. I like to give this analogy that everyone is eating rice, but we know that rice contains arsenic, which is dangerous, but it contains so small pieces that it's still fine to eat rice. So as long as even if wireless signal would in more doses be dangerous, we have these limits on things. And what this happen, or what the point with all of this beam forming is not to make the density higher in the best cases than in the past. If you were standing in front of the base station, you have an antenna today focusing on you. It's not to increase that number, but rather to make sure that at other places you're raising the signal density to that level. So it's not about really increasing the radiation. It's more making sure that it appears where you want it to be.
Excuse me, I'm Mahadevan here.
Thank you.
One of the main reasons is the hazard. So even if there is a focused beam, the effective isotropic radiated power can be controlled so that you are well within the hazard. So because the main problem is because of the focused beams. Because the focused beam, if you keep the same power throughout, then the hazard may be increasing, and the standards are different in different countries. So this is one very major area where not much study has really come out in public. So because it is different for different people, but the hazard is very, very significant, specifically in millimeter waves.
I mean, we are following the same limits as in the past. So when we are adding more antennas to get more directivity, when you deploy this in reality, you need to cut down on the power so that the maximum ERP that you are having still have the same limit as before.
Thank you very much for the excellent session.
Yeah.
Thank you.
Okay, should I take another question here, or?
Yeah, thank you. Professor, one more question is there actually in the chat window. Actually, how feasible it is optimize the beam forcing from the IRS in the dense multiple network?
So yeah, I'm not really finding that question.
Okay, yes. The dense optimize, how feasible it is to optimize the beam forming from IRF in the beam dense multi-user network.
Okay, yeah. Yeah, this is a good question. And I am one of those who are a bit skeptical towards the greatness of that technology, in terms of that some people have been selling it as this is the main best thing for everything. And now I am sure that you can build this, you can configure the IRS. The issue is how quickly can you configure it. In this experiment that we were doing, it worked out fine. So you can build it, but I don't think it is a technology for high mobility use cases. I think you need to use certain structure about things. So yeah, it is feasible, but maybe not for high mobility situations. But a lot of the data is consumed by people who are indoor or at fixed locations. So I think there are still good use cases for it.
Yeah. Thank you, sir. Thanks for your wonderful time, and it was very useful for all the participants. Actually, it was very nice session. So, just we will take another 2 minutes. Our student will conclude. Actually, Surabhi, yeah, please go ahead.
One more thing. So can we get the reference of the books which you are saying, which you are quoting?
Yes, exactly. So I have that
you
here.
can post it to them. They can forward it to us.
Yes.
Yeah, they are all very relevant books for this topic. So possibly you can pass it on to them, Dr. Parameshwarappa, and they will pass it on to us.
Yes. So both of all of these books are available. Actually, you can download PDFs. So
Yes, Archita, you please go ahead.
Yes. It was such a thoughtful webinar. I hope the knowledge gained by this webinar would be fruitful to all the young minds present here. As we come to an end of the webinar, I request Purti B to render the vote of thanks.
It was a great webinar, sir. I extend my heartfelt thanks to Dr. Emil Björnson, sir, for the great information. Thank you, sir. I would like to extend my thanks to Dr. Deepa Shanai, Chair, IEEE Bangalore Section, and Professor UVCE Bangalore. Thank you, ma'am. I would like to thank Dr. Parameshachari BD, Professor and Head of the Department of Telecommunication Engineering, Chair, IEEE Mysore Subsection, and IEEE Student Branch, Counselor GSSS ITW Mysore, for the constant support. Thank you, sir. I thank all the office bearers and the executive members of IEEE Mysore Subsection, IEEE Bangalore Section, IEEE Information Theory Society Bangalore Chapter, IEEE Circuits and System Society Bangalore Chapter for conducting this webinar and constant support. I once again thank all those who are present and making this webinar successful. Thank you.
Yeah. Once again, thank you, sir. Thanks for your wonderful speech. I thank all the participants for joining us for today's webinar. So kindly download the certificate which we are given in the feedback links. Thank you all.
Very much. And
But-
yeah, for those who, if someone didn't get an answer to the question, please feel free to drop me an email and I will try to answer it offline. Thank you.
Thank you all and have a great evening.
Thank you.